Hello. All right. How are you doing? All right. So who had a chance to look at the simple harmonic motion? Yeah, me too. The chance to look at simple harmonic motion, the assignment. Just printed. Excellent. Anyone else? Okay, good. Right, so simple harmonic motion. So have you done it in school? Yes or no? Have you done simple harmonic motion in school? No, this is a new topic for you. All right. So the simple harmonic motion is quite straightforward. Well, I mean, it's not quite straightforward. If you take a pendulum and you swing, that is approximately simple harmonic motion. Or you have a mass on a spring bouncing up and down. That's approximately simple harmonic motion. If you're on a trampoline and you jump, but not if you don't actually jump, if you just bounce on a trampoline without losing contact, that's simple harmonic motion. You take a ball like this and a marble, or like in my case, a AA battery, and you let it go, and it bounces. Yeah, so this bouncing act is approximately simple harmonic motion. So simple harmonic motion is basically oscillations. It's a very particular type of oscillation in which the returning force, so when you displace something from the mean position, if you displace something, there's a force returning it to the original position. So let's have a look. I'll share my screen. If you have a mass on a spring, and you have and there's a spring. With spring constant K, and you pull the mass to the right. So this is the equilibrium position. This is the zero position. If you pull the mass to the right, there's a force returning it to the left. If you pull the mass to the left, there will be a force to the right. Okay, is that clear? Is that restoring force? If the object is displaced, if the mass is displaced, there will be a restoring force, that will attempt, or that will push it, which will push it back to equilibrium. Equilibrium. And the definition of simple harmonic motion, an object performs simple harmonic motion if the restoring force is proportional to displacement. Is that clear? That the restoring force, that the force is proportional to displacement. So the further you pull it away, the stronger the force. The further you displace that, the stronger the force. Right. Okay, so no questions here. So you understand what that means. So we understand the definition. You need to be very clear on the definitions. If there's something you don't understand, please let me know. Now, of course, force is in the opposite direction of displacement. So we say force is proportional to minus x, or yes. But we also know that force is mass times acceleration. So mass acceleration is proportional to minus x. We can divide by m, and we can say that a is proportional to minus x. I mean, without losing the proportionality. Okay, m is constant, so we can divide by m. So we say that from here, we say in simple, the equation of simple harmonic motion is acceleration equal minus omega squared x, where omega is a constant. And omega squared just ensures that it is positive, where omega is a constant. Now, this omega is not a random constant. It has a meaning, of course, and the meaning is its angular frequency. Is angular frequency. Now, F is frequency. F is frequency. When we know frequency is how many oscillations per second, right? How many oscillations per second? So, well, the angular frequency is going to be 2 pi f. So basically, it's pretty much the same as the frequency, just multiplied by 2 pi. Okay. So if the frequency is I don't know, 3 hertz, there's 3 oscillations per second, then the angular frequency is going to be 2 pi times that. So it's going to be 3 pi. So it's 9.42 radians per second. Or simply, you can say it's 9.42 second to the power minus 1. So these are equivalent. Just keep that in mind, that this radians per second and second is second to the power minus 1. These are equivalent because radian, in physics, radian doesn't have a value, doesn't have a meaning, a physical meaning to it. Okay. 942, because that's 3.14 times 3, if I'm not mistaken, times 3. Yes, 9.42. I haven't missed it. Everything clear so far? Okay, very good. Now, another example of simple harmonic motion. You're probably right, Edith. Yes, it is, of course. Sorry. It is 6 pi. It is 18.84. 18.84. Thank you. Radians per second. Now, so angular frequency is just, well, it's a very convenient way of thinking about frequency. Yeah, it's not the actual angle per second. It's not the angle through which it swipes per second, like the pendulum. It's not like that. It's just a convenient way to mathematically assess the oscillations. Now, let's say you have a pendulum, and when the pendulum is at the bottom of the swing, it has two forces. So that there's a tension force and there's the mg force. So there's no resultant force. But when the pendulum is displaced by x, from the equilibrium position, so this is the equilibrium position, this is the displacement, so this is x. When the pendulum is displaced by x, there is a restoring force, and let's have a look where it comes from. So there's the weight mg, and there's the tension force. And if you add these two forces using so this is the tension force, this is the mg, and if you find this is the restoring force. So this is the restoring force. There's the force attempting to return the pendulum back to the original position. So in this case, the restoring force is proportional to minus x. But this only works for small displacement. Only for small displacement. Displacements. Okay, and it is shown in the assignment why that is only works for small displacements, because you have to use the small angle approximations for this to be true. Okay, so let's have a look at this equation, because this is a very important equation. It looks incredibly simple, but it has such a fantastic, there's a lot of maths in here. Okay, so we know that acceleration is the derivative of velocity. So we know that acceleration is the derivative of velocity dt. So it can be written as v with a dot. Dot means derivative with respect to time. And velocity is the derivative of displacement dx dt. That means it's x dot. Now, because v is x dot, this is x dot with a dot. We use it as x double dot. We write it as x double dot. X double dot literally means second derivative with respect to time. Dx dt squared. Does that make sense? It's not the first time you're seeing it, right? Does it make sense? Yes or no? Acceleration is x double dot. So we can rewrite this equation. The acceleration is minus omega squared x. We can rewrite it as x double dot equals minus omega squared x. This is the equation of simple harmonic motion. Equation of simple harmonic motion. Why? Well, because of the definition. It's by definition. It's definition. It's the equation of simple harmonic motion by definition. The definition of simple harmonic motion is that the restoring force is proportional to the displacement. So let's have a look at the first problem. Show that a cos omega t plus phi is a solution to x double dot equals minus omega squared x. So x is a solution. Well, this is a differential equation. A differential equation that contains x, which is a function of t. So this is a differential equation. Differential equation. In a normal equation, you're looking for the value of the unknown. Here, you're looking for the value for the unknown function. X is the unknown function. Okay. If I give you an equation like x plus 3 equals 8. Even if you don't know much about equations, you can guess. You can guess that x is 5, right? Because you know that if you put 5 into the equation, it works. So the question is, what do you need to put instead of x to make this true? Right. So just like in this example, what does x need to be to make this true? Well, x equals 0 obviously is a solution, but we're not interested in that. X equals 0 means that it's just a stationary object. Yes, a stationary object will remain stationary. So x equals 0 is a solution, but not a particularly interesting one. So it turns out that one of the solutions is this. So xt is a cos omega t is one of the solutions. Is a solution. So it turns out x equals a cos omega t plus phi is a solution. And to prove that it is a solution, well, it's not really proof, it's show that. We're showing that it is a solution. Now we're differentiating it. Derivative of x. Now we're using the chain rule here. So it's going to be a omega multiplied by minus sine omega t plus phi. Right. Okay, so please let me know if it is unclear how I got this. Don't be shy, it's a new thing for you. If you'd like me to explain better, I'm happy to do that. Do you understand how I got this result? Okay. So imagine you have y is equal to cos 3x plus 2. If you want to find the derivative, that would be 3 sine 3x plus 2. Is using the chain rule. And there will be a minus here. We have x equal a cos omega t plus phi. X dot, which is the derivative, just like that, and that's going to be a times omega, because that's the omega is the 3, sine omega t plus phi. And there's a minus, of course. Right? Does that make it clear? Okay. So I can take the minus out. Minus. And now I find the second derivative. I differentiate it again. When I differentiate it again, I have another omega coming out because these are constants. So we have another omega. So it's going to be minus a omega squared cos omega t plus phi. And now we substitute that into the original equation. We substitute x into here. We substitute x double dot into here. So substituting into, let's call it 1. We have minus a omega squared cos omega t plus phi is equal to minus omega squared multiplied by a cos omega t plus phi. And you can easily see that this is true. True. Therefore, x equals a cos omega t plus phi is a solution. Okay. Now, let's look at these. Let's look at these closely. So this is the displacement. The first one is the displacement. The second one is the velocity. And the last one is acceleration. Okay. Well, we know cosine. Cosine changes from -1 to 1. The same with sine. So what is the maximum value of x? X max. The maximum value of x. The maximum value of displacement is a, of course, because when cosine is equal to 1, x will be a. Is the amplitude A is the amplitude. The maximum displacement is the amplitude. This is velocity, right? This is velocity. So what is V max? Oh, yes, it is O. Because the maximum, look, sign can only change from -1 to 1. So this is maximum when this is, well, -1. So it's A omega. O. Okay. The maximum velocity is A omega. And X double dot is acceleration. Yes, the maximum acceleration is A omega squared. So as you can see, omega is a very convenient metric, is a convenient parameter for an oscillator. This is the acceleration. Okay, so phi, on the other hand, is called the phase. Phi is known as the initial phase. Basically, it answers the question, what is the oscillator doing at the very beginning? So where does it start? It is determined by the starting position, determined by the starting position. Okay. So the oscillator starts from maximum velocity. There are different ways you can do that. I'm going to do the simple way. I won't use the maximum velocity. I won't use this because I don't really want to confuse you. What you need to understand that when velocity is maximum, if you have a pendulum, what is the displacement when velocity is maximum? What is the displacement when velocity is maximum? Velocity is maximum is at the middle, yes. Velocity is maximum when displacement is 0. Thank you. That is true. So velocity is max when x is 0. So basically what it says that when the oscillator starts from maximum velocity, when t is 0, x is 0. So we write down the equation. X of 0 equals a cos omega times 0 plus phi, and that's equal to 0. So that means a cos phi is 0. So cos phi is 0. 0. So phi is pi over 2. Over 2. So we have x of t is equal to the amplitude multiplied by cos omega t plus pi over 2. And if you look, cos omega t plus pi over 2, it's going to be minus a sine omega t, because cos x plus pi over 2 is minus sine x. You can prove that. I'm not going to spend time proving that, but because I hope you remember that from the trigonometry assignment. All right. And 2. Oh, sorry, not 2. B. It says it starts from maximum displacement. So basically it says when t is 0, x is going to be a maximum displacement. That means that x of 0 is equal to a cos omega times 0 plus phi equals a. So that means cos phi is equal to 1. So phi is equal to 0. So the equation becomes x of t is a cos omega t. And the previous one was x of t equals minus a sine omega t. Right. So these are the solutions. So the phi determines where you start the oscillation, where you start the cycle. If you start the cycle at maximum displacement, that's phi equals 0. If you start it at the middle, it's pi over 2. It's a quarter of the cycle. Okay. So it's the starting phase. A phase is, well, it's the phase of an oscillation. It's where you start. So that hope that makes sense. I have to say I really enjoy this topic because it's an amazing combination of physics and maths, because differential equation, it just gets me really excited when I teach this topic and when I do problems on this topic. Now, what we haven't explored yet, well, we've found the link between omega and frequency, and we just need to remember that frequency is 1 over time period. So you should know this from the waves topic from school. You know that frequency is also 1 divided by the time period. So in other words, time period is 1 over frequency. And frequency is omega over 2 pi. So that's going to be 2 pi over omega. So frequency is 1 over time period, and time period is 2 pi over frequency, as I have already mentioned. So I'll just frame that. So a mass, when hung stationary by a spring, extends by delta L. Well, you know what? Before doing that, actually, let's do this one. for the mass on a spring? Well, we know the force. So every problem on simple harmonic motion is done in the same way. So first, algorithm to solve problems on simple harmonic motion. First, displace the mass by x. 2, find the resultant force. The resultant force in terms of x. Compare your equation with x double dot equals minus omega squared x to find omega. So hopefully this will make sense in a bit. So this is the algorithm to solve problems on simple harmonic motion. In most problems, you need to find the time period. So this is to find the time period. Fine. Okay. So I displace the mass. So I move the mass to the right. So I have displaced the mass by x. What is the force? What is the force on the mass now, once it's displaced? Minus kx, yes. The force is minus kx. So mass acceleration is equal to minus kx, because Newton's second law, force is mass acceleration. And mass acceleration is minus kx. That's the only force on the mass. Divide by m, so we got acceleration is equal to minus k over m x. Right. So we've done 2. Compare your equation with x with a equals minus omega squared x. Comparing these two equations, we can see that omega squared is equal to k over m. Right, do you understand? Does everyone understand? Please let me know. I'd like to see an answer from everyone. Okay, so we've established that omega squared is k over m. So omega is square root of k over m. We don't care about the negative because it can't be negative. It's a frequency. And then finally we can say, well, time period is 2 pi over omega. That is going to be 2 pi multiplied by k, m over k. So the time period of a mass spring system, is 2 pi square root of k over m. And you can use this result to find the time periods of other systems. It is m over k, yes. It is m over k. And it makes sense. If you increase the mass, the time period increases. If the pendulum is heavier, it will go slower. If the spring is stiffer, if you have a stiffer spring, it will oscillate faster. It will take less time for an oscillation. And this brings me to an interesting fact, like astronauts on a space station. Obviously, they can't use bathroom scales, because they won't work. They're weightless, although they're not weightless. They do have weight. The correct word is normal reactionlessness. It just doesn't sound, it sounds like a mouthful. The bathroom scales, but when you stand on bathroom scales, they're not measuring your weight. They're measuring your normal reaction force. I know. And measuring your normal reaction force. And if you're in space, and you're orbiting the planet, there's no normal reaction because you're floating in the ship. There's no normal reaction, and you can't measure it. So what they do is they have a spring. They attach themselves to a spring of known. When they want to find their mass, they attach themselves to a spring of known spring constant, and they start oscillating. And they measure the period of these oscillations, and this allows them to calculate their mass. And body mass is an important factor because when you're in space, you are losing muscle. You're losing your muscles because you're not using them as much as you are using them on Earth. And so astronauts constantly, especially if they spend months in orbit, they constantly measure their mass just to keep healthy and not to suffer too much when they come back down to Earth because they forgot how to use their legs. Okay. So yeah, that's an interesting fact about astronauts. So, and using this algorithm, we're going to use that a lot. Well, I'll probably do another webinar next week on the same topic because it's a big topic. When hung stationary by a spring extends the spring by delta L, find the period of vertical oscillations of the mass on the spring. Okay, so the setup, we have a mass spring system. So this is a mass. And when it is hung stationary, the spring extends by delta L. Okay, so we hang the mass and it extends by delta L. So compared to the non-extended position, let's say it was here, now extended by delta L. That means that the force in the spring is K delta L. So mg, the force of gravity, is equal to K delta L. I don't need to use any minuses here because, well, yeah, we obviously understand mg is positive, K delta L is positive. They're both positive. That's fine. We don't need minus. Okay, so mg is K delta L. So we can, and we know that the time period of a mass spring system is 2 pi square root m over k. We can do several things here. We can make m the subject here and substitute it in. What I would recommend, because we are looking for the unknown ratio, the ratio of m over k. So we divide by k. M over k is delta L over G. And m over k, delta L over G, we can substitute. So 2 pi square root delta L over G. And if you've done any simple harmonic motion, you should recognize this formula. Do you recognize this formula? If you have a pendulum of length L, and the gravitational field is G, the time period of a pendulum is 2 pi square root L over G. It looks very familiar. It's not the same thing, but it just looks very, very familiar. Okay, they look very similar. Although that's the extension of this spring. Yeah, this is the time period of a pendulum. By the way, if you take a pendulum of length 1 meter, let's find the time period. Time period of a 1 meter pendulum. So the time period is 2 pi multiplied by square root of 1 over 9.81. That's going to be 2 pi square root 1 over 9.81. That's 2.006. That's how the second was defined. The second was defined as half of the swing of a 1 meter pendulum. Or is the other way around? 1 meter was defined as the length of a pendulum that took 2 seconds. No, I'm pretty sure it's the other way around. We have now a different definition of second. And if you do this experiment, do it at home. Take a piece of rope, measure one meter, tie something heavy to it. It needs to be heavy because it needs to be heavy enough for the mass to ignore. Take exactly 1 meter and, I don't know, tie an AA battery. That's good enough. Take a 1 meter rope, and a AA battery, and start swinging it. And measure how long it takes for one's complete swing. It should be 2 seconds. Let's see how close you can get to 2.006. Right, you should. No, that wasn't Newton. Sorry, I don't remember. I don't remember who it was who defined that. You can of course search it up, but yeah, I mean that's something like do it at home, like the pendulum takes 2 seconds. Okay, so and that's it. Yes, find the period of vertical oscillations of the mass on a spring. So it's this. Newtons. Okay. Now this is problem. This was problem 2. This is problem 3. Find the period of oscillations of the 3 oscillators. Does the period depend on the distance between the walls in C? Okay, so let's have a look. Now, we say that these springs are in parallel. Yeah, so A, B, C. So in A, springs in parallel. And for springs in parallel, you can prove that K is equal to K1 plus K2. So you don't have okay. I'm just wondering how much time I have, how deep I want to go into this problem. For springs in parallel, is K equals K total is K1 plus K2. K total is K1 plus K2. Does that make sense? Well, yeah, because both springs push are extended by the same length. They push proportional to X. For B, springs are in series. And K, the total, 1 over K total, is 1 over K1 plus 1 over K2. Did you know this? Did you know this, or this is new information to you guys? Okay. Beautiful. Okay, that's really good, because I don't need to go too deep into this, because I wanted to explain why. So, but since you understand that, but you can prove that. It's not very difficult to prove. But yeah, it's just, and because we already know the time period is 2 pi square root of m over k, and that becomes really straightforward. In the first instance of A, the time period of oscillator A is 2 pi square root m over k1 plus k2. TB is going to be 2 pi square root. So now K, the total K is K1, K2 divided by K1 plus K2. So that would be M multiplied by K1 plus K2 divided by K1, K2. And in C, what do you think in C? Is that parallel or series or neither? in C, would you call that parallel or series? Or neither? Okay, let's look at what defines parallel or in series. So let's say if we move the mass by x to the right. Now x1 extends by x, so the spring 1 extends by x1, and the spring 2, k2, extends by x2, and the mass shifts by x. But in this case, x1 has to equal to x2, and it has to equal to x. This is the case for parallel springs. Now for this spring, the first spring extends by x1, the second spring extends by x2, and the mass moves by x, and x is equal to x1 plus x2. That's for series springs. Which one do you see here? Is that this situation, or is it this situation? Is the displacement of the mass the total displacement of the springs, or it is parallel? Yes. So it wouldn't be any different if we move that spring onto the other side. Look, if we move this spring over to this side, it won't be any difference. It's the same thing. It's a parallel. It's a parallel combination of springs. So in parallel. And of course, the time period is the same as A. So TC is equal to TA. Does everyone understand? Yeah, so here I have x equals to x1 equals to x2. Because if you shift one spring, the other one shifts as well by the same amount, by the same distance. Hello? You still with me? Another new thing to me. Yeah. Makes sense. Well, I mean, if you look at an analogy with electrical circuits, no, I won't go there. I can't immediately see it, how it translates to electrical circuits. So yeah, so TA is equal to TA, and that is 2 pi square root m over k1 plus k2. Good half an hour left. Well, I'll attempt to okay. Let's look at this question. Oh, why am I? Let's start with this one. This one is problem 6. So I'm going to label them. Anyways, let's start with this one. Find the period of small oscillations of the pendulum if the dolly is accelerating at a constant rate A. So the dolly is accelerating, and it's a heavy dolly. So what difference does it make that it is heavy? Well, if it's heavy, that means the pendulum can't make the dolly swing. Right? If the pendulum swings, the dolly stays where it is. Right? If the dolly was light or comparable to the pendulum would swing and the dolly would swing around as well. Right? I mean, imagine you're on a swing which is not fixed to the ground. You swing and the swing moves as well. Find the period of small oscillations of the pendulum. Now, we know that the time period, so the time period of a pendulum is 2 pi square root of L over G. So L is L, obviously, but what is G? It is accelerating. The easiest way to look at this problem is to think about this. Gravity, and this is one of the Einstein's discoveries, that imagine 2 situations. You're in your house, and the gravitational field is 9.81. And you're sitting on the floor. Oh, I don't know, playing Legos. That's what I normally do. You feel that you don't feel gravity. Like, honestly, people don't feel gravity. People feel something hard pushing against their bottom. That's the ground. That's what you feel, actually. So when you're sitting on the floor, you feel the ground pushing you from the bottom. The ground is pushing you. That's the normal reaction force, and that's the force that you feel. It's the normal reaction force pushing you up. And if you drop something, it falls to the ground because it accelerates towards the ground. That's situation number 1. Situation number 2, you're in a rocket. You're in a rocket. There's no gravity. You're in deep space. But the rocket is accelerating at 9.81 meters per second squared. 9.81 meters per second squared. Newtons per kilogram. You have gravity, and here you have acceleration. If you're sitting on the floor of the rocket, so if it's a really, really quiet rocket, and there's no noise from the engine, you wouldn't be able to tell the difference. You would feel exactly the same way. You're sitting on the floor is pushing you from the bottom. If you drop something, it will accelerate towards the floor at 9.81 meters per second squared. Right? Because, well, it's not the thing remains stationary. The rocket is accelerating towards the thing that you drop. So if you drop something, the floor of the rocket accelerates towards it. Basically, you would not be able to tell the difference if you are in a stationary rocket on Earth or you are in an accelerating rocket in space. And one of the this is one of the Einstein's. They say it's one of his most wonderful thoughts. During his life, that he realized that it's the same thing. So if you are in an accelerating dolly, if you're on top of an accelerating dolly, it would feel the same as if the gravity was not vertically downwards, but if the gravity was sideways, was like this. Does that make sense? If you're in a dolly that is accelerating forward and you were in a closed compartment, you would see that the pendulum would be in this position, right? Normally it would be in this position. It would be the same as if the gravity had a slightly different direction. Do you understand? Just say yes or no, please. Right. So feels like the gravity is like this. And let's call it perceived gravity. G is perceived gravity. And of course, it is made up of two components, the horizontal component and the vertical component. The vertical component is G, as expected. This is G, and this component is A, is the acceleration. So G star is square root G squared plus A squared. Therefore, the pendulum would be sideways, but it would be oscillating left and right like this. And the time period, G star, is going to be 2 pi square root of L divided by square root of G squared plus A squared. And we can just make it slightly prettier. It's going to be 2 pi 4th root of L squared divided by G squared plus A squared. So this is the answer. So not a difficult question. Like, I mean, difficult to understand the underlying physics behind it, but no complicated calculations. So I hope that makes a lot of sense. Any questions? Happy to answer. I've been a talking head for an hour, 10 minutes. Not that I don't enjoy it, I do, but I enjoy even more when you have questions. So one of the questions involves a dolly rolling down a ramp in the assignment. So it's the same situation. Yeah, so I basically solved it for you. Just need to work out the acceleration. And acceleration would be G sine theta. So yeah. And this dolly is it looks like a very similar one, yet it is very different. It's a very different problem. So here, the mass of the pendulum is m, the mass of the dolly is capital M, and they are oscillating, and the ball is oscillating. And in this case, the dolly is not considered heavy. That means when the pendulum starts swinging, the dolly will start swaying as well. It will sway with the same period, with the same period, with the same frequency. Basically, which principle of physics can be applied here? We had a whole assignment on it. Can somebody think of which physical principle? Conservation of momentum, yes. And can you be a bit more specific? Which part of conservation of momentum we are going to use? Is that internal forces cannot change the position of the center of mass. Yeah, internal forces, and here we don't have any external forces. Internal forces cannot change the position. So basically the center of mass would stay where it is. So what does that mean? That means that when the dolly is here and the pendulum is here, let's say the center of mass, let's say it is here. It's the position of the center of mass. Of central mass. Of mass. Okay. And when it shifts, it goes like this. But the center of mass stays where it is. So basically, you have a swinging like this. This point remains stationary. This point remains stationary. Now, I have solved this problem before in the webinar last year. You can access the webinars from last year. And basically what happens is the length of the pendulum is L, but you need to find the effective length. This is L star. L star is the effective length. And the time period is going to be 2 pi square root of L star over G. And the effective length, you just need to find the position of the center of mass and work out this part of the length, and that's it. That's the time period. And then to find the speed, well, it's the speed is V max is omega A. So that's easy. You can work that out. But this is what we need. Okay. So we need the time period, so we need omega. So omega, of course, omega is square root of G over L. And L is a fraction of the whole length. So it's going to be M over M plus M L, I believe so, L star. And yeah, that's it. So basically the dolly would move right and left, right? and they swing, the pendulum would go right and left, and they would go in opposite direction. They would go in counter phase. But this point on the rope would remain stationary. So if you take a video, the point remains stationary and they kind of move to either side of each other. And because this is because the center of mass cannot change position in the absence of external forces. So you find the position of the center of mass, you work out L star, and then you find the omega, which is square root of G over L star, and then you do the maximum velocity is omega times the amplitude. Is that clear? I'm not doing the whole problem. I'm just showing you how to do it. And there's a problem, and there is a problem like this in the assignment. But the realization. And the last thing I would like to go through with you, it's one of my favorite questions ever, like ever, because I had this question on my entrance exam to university, which was a long time ago, around the time you were born, probably. And so yeah, a hole is drilled through the earth via the poles. Okay. Like a shaft. A small stone is thrown, ignoring air resistance. Haha, I mean, probably going to be a very fast stone. You can't ignore air resistance when you throw a stone from a bridge, and yet you're throwing it from the pole. Anyways, ignoring air resistance, how long will it take to reach the center of the earth? At what speed will it be traveling at the center? Okay, so when we are at the top, the force is mg. At the top, the force is mg. And that makes sense. That's the only force that causes it to accelerate down. mg. Let's try to imagine how this force changes with x. So let's say this is the x-axis. X-axis. This is the 0 on the x-axis. And this is minus r and r. So this is the force, and this is the x-axis. So we know that when the distance is minus r, the force is mg. What do you think would happen? What is the force when x is 0? What is the gravitational force when you are at the center? Indeed, yeah, it is. It is 0 because you're being pulled equally in all directions. And what is the force when you are at the maximum position, when you are at r? Minus mg, yeah, very good. Minus mg. So we've got 3 points. And I just want you to believe me, like there is obviously a reason, because so it turns out that this force is linear. And I do want you just to believe my word, because it will take a long time to explain why it is. But it makes perfect sense. Like say you are in the, like say you are here. It turns out that you're being attracted by this part of the earth. This part of the earth pulls you down. But then there's a special law called Gauss's law. It turns out that you're only being affected by the gravity of the inner part of the earth. But this part of the earth pulls you down, but this part of the earth pulls you up. And it turns out that they compensate. So the part of the earth that pulls you down, which is below this part, the gravitational pull of this part of the earth, and the gravitational pull of this part of the earth are compensated. And when you are at a depth, when you are at distance x from the center of the planet, you're only being pulled down by what's beneath you, as in inside the imaginary sphere. Okay. So in other words, we can find the acceleration. We can find the force. Force is equal to, well, the gradient. Well, we find the gradient is minus, and the gradient of this line is mg over r, minus mg over r, multiplied by x. And this is equal to mass acceleration. Equal to mass acceleration. So you can see that acceleration is equal to minus g over r times x. Do you all understand where I got this from? I found the gradient of the line. So this is a straight line with gradient mg over r, minus mg over r, and I found the straight line. MA, so I found this equation. So I have omega squared is, because I'm comparing it to a equals minus omega squared x, omega squared is g over r. Right. So that means that the time period is 2 pi over omega, which is 2 pi r over g. The time. So basically what would happen, the stone would fall, it would reach the middle, continue moving, reach the other end, and then go back again. The stone would oscillate back and forth inside the hollow tube. It would go from the North Pole to the South Pole and back again. It will keep doing that. And the time period is 2 pi r over g, which looks very familiar. What does it look like? It looks like the period of a pendulum of length r, which is the radius of the earth. So if you had a pendulum which had length equal to the length of the earth, it would have the same time period. And let's calculate that time period. Calculate the time period, and that's because we know the period of the earth, so it's 2 pi square root 6400000 divided by g, which is 9.81, 2 pi multiplied by square root 0 divided by 0.81. 5,075 seconds. And how long will it take to reach the Earth? Well, the time period, the whole time period is the whole cycle. It goes forwards and backwards, all the way back to the top. So the time to reach the center is how much? Anyone? So if you start at the top, go to the center. Yes, Alexander, thank you. It's T/4. Of course, it's a quarter of the time period. It takes about, divided by 4, 1,270 seconds. 1,270 seconds. And I don't know if that's what. How long does it take? That's 5,075 seconds. 5,075 divided by minus 3,600. 1475 divided by 60. That's 1 hour. 1 hour, 25 minutes. 1 hour, 25 minutes. So it turns out the stone would fall to the center of the Earth, reach the other end of the planet, and go all the way back in just 1 hour, 25 minutes. And you know what? This number looks familiar. That number looks familiar. How long to orbit the Earth? That's the wrong question. Okay. How long does it take the ISS? 90 minutes. Yeah, so if they start at the same time, if you throw a stone and the ISS is flying above you, above your head, by the time the stone reaches the South Pole, ISS would be at the South Pole. And when the stone reaches the original position, you would have the ISS back at the original position. It's not a coincidence. I would say more if you had a shaft drilled not through the center of the Earth, but you had a shaft drilled like this. And if you make a railroad track along this tunnel, if you build a tunnel which is straight, like tunnels are not straight. I don't know if you realized tunnels are not straight. They have to follow the curvature of the Earth, or actually they actually go uphill slightly and then go downhill, so the water doesn't stay in the middle. But if you had a straight tunnel and you release a train from point A to point B, the train would accelerate because it's kind of going towards the center of the Earth. until this point, and then it would decelerate. So accelerate and decelerate, decelerate. And no matter where point A and B is, A and B, no matter where A and B are on the surface of the planet, it could be a train from London to Sydney, it could be a train from London to Paris, it could be a train from London to New York, it would always take exactly the same time, half of the time that we had. So 1 hour 25 is about 42 minutes approximately. 42 minutes. So yeah. So seemingly a random topic, like drilling a hole through the earth, and simple harmonic motion pops up. I love this. I hope I managed to share some of the excitement for this topic to you. Hope you enjoyed today. If you find my other webinar, which has very similar problems, but a slightly different approach, so do find my other webinar on the same topic from last year. All right, enjoy doing the problems, and see you next week. Welcome.